Good afternoon, ladies and gentlemen. Welcome after the break. Our second session today will be devoted to hydrogen vehicles and equipment and companies that get ready to the manufacturing of those. And our first guest today is the manufacturer of the first hydrogen car registered in Poland, Dr. Andrzej Szałek. Thank you very much, ladies and gentlemen. Ladies and gentlemen, in my presentation, I would like to show you the path that Toyota has covered to produce hydrogen drives, and also to present to you what future we see related to it and how we see its applications in the future. The hydrogen project in Toyota started in 1992. Well, actually, that was the year when we started three parallel projects. One, the one that I mentioned, hydrogen drive, the other concerning a hybrid drive, and the third one concerning a vehicle whose source of power would be high-voltage battery. In 2002, we demonstrated our first car with hydrogen drive, whilst in 2008, we presented a car fully designed by Toyota with Toyota's drive and the one that we offered to a selected group of consumers. In 2014, we offered the first series car, Toyota Mirai. Mirai stands for future in Japanese. It was shown in Japan only, then found its way to Europe and the USA. It is fully electric, zero emission, 155 horsepower. Its maximum torque is 330 Newton-meters. After filling it up, or actually charging it up, the range of the car is 550 kilometers. Why? Because in 2020, we presented the other generation of Toyota Mirai. Let me pay attention that it is a car that is a class higher. It has a totally new drive. You will not find any elements of the first generation Toyota drive in it. Its power is 182 HP. I'm talking about it because that's the most frequently asked question. I have it written down here to be able to answer this question. Maximum torque, 300 Newton-meters. And the most important data, the range, after refueling, that lasts 3 to 5 minutes, depending on the operator's efficiency. Like in the usual car, the range is 800 kilometers. So we have a car that is purely electrical. And it has the range of the one similar to the cars that we normally use. It's not only zero emission, but it also purifies the air. How come? We take care of the fuel cell in the car. We want to prolong the life cycle of the fuel cell even further, so we purify the air that gets to the cell, and after 10,000 kilometers covered, the car cleans that much air that is needed by a single person to breathe for a year. Why sedan? Well, actually, this is the most popular body. I'm talking here about the model of the body of the car, and it uses the fewest, the least amount of fuel. Choosing this body placed our challenge really high, because all the elements that we need to use to build it are the elements that need to be much smaller than the ones that we would use on a regular SUV. So that challenge, on the other hand, makes it possible for us to use different kinds of drives. And right from the beginning, constructing this drive, we assumed it to be scalable. So not only to a passenger's car, but also to all sorts of different kinds of drives. Now, how come that in such a short time we were able to design from scratch a hydrogen drive and become the owner of patents for it and its manufacturer? It's owing to the hybrid drive that constituted the basis for us to create a hydrogen one. It happens not just in our company. When you have a look around the manufacturers of hydrogen cars, all of these manufacturers are also mass manufacturers of hybrid cars. It is the hybrid energy management that made it possible to create a hydrogen car. By the way, apart from the patents concerning hydrogen, we also got those pertaining to hydrogen drives. No other company was able to actually evolve without getting patents on hybrid drives. Well, you need to really be specialized to be able to manage such drives. That was our need at the moment, and that is what enabled us to create this car over such a time span. We have two types of tanks volume. It's prolonged the designing period, but on the other hand, it makes it possible to apply it on different cars. Right from the beginning, we assumed that this drive is going to be scalable. Now, another generation, so the second generation of Toyota Mirai that you have had a chance to see during the break, is a car that has three tanks, three different tanks, and also their structure is different compared to the first generation. The tanks have a rarer set of coal fibers, and they result in the smaller weight of those tanks. So again, I repeat that the car has been designed from scratch, no elements repeated from generation 1 Mirai. The fuel cells that we used in 2008, so on the first model, where we already had our own drive, the fuel cells had the density 1.4 kilowatt per liter in 2015. So the European model was 3.1. That was the highest value in the market that you could achieve at that point in time. So we have a far greater density of power. But what is important is that in the right fuel cell or fuel cell stack, we have 400 cells. In this new generation, 370, with the power was much higher. It results from a far greater efficiency of the fuel cells that was subject to patenting and that we applied in Mirai Generation 1. So what is the core of the efficiency of fuel cells? As a byproduct, they generate humidity, moist vapor that makes it harder for energy to flow. Using those little canals, those spaces, is a very quick way to get rid of the moist and to move energy across in the fuel cell. The humidity taken away from it is reused to moisturize the fuel cell. It requires to be moisturized to act. So we also laminated the moisturizing unit. We increased the efficiency, we reduced its volume, and we increased its volumetric power. Why, ladies and gentlemen, looking at the development of automotive industry in 130 years, why did this kind of drive come so late? Well, the problem was how to create tanks that will not undergo corrosion, that will be safe to use for transportation. Creating of the material that you can see inside, again patented by Toyota, using carbon and glass fiber. The way of joining the materials made it possible for us to create those that have permeability of laboratory volumes. They are really safe. I often show this slide to make a point that there were even attempts at shooting at the tanks from weapons. It was not of that scale, but still I want to make it clear that no tank has been verified with sachet test, and those have been. So the test was adequate to see how effective in protecting the contents they are, comparable to checking the quality of the armor in the army. And the pressure 150 tons. I don't know of any other tank that would be able to withstand such a load, so I would like to say that those cars are really safe.
The car was introduced into 2014 to the Japanese market. We expected 400 orders, and we got over 1,500. It's important that over 40% of orders came from individual customers, which means that there is a huge purchasing power in the market. There is a huge demand for this kind of the drive. In the US, before it was introduced, the cars with this drive were introduced, we already had 2,000 orders. So our plans that envisaged 350 units a year were verified. In 2017, we reached the maximum level of 3,000 units. Now, creating the new structure of the cells that are used in Toyota Mirai Generation 2, building another manufacturing plant made it possible for us to produce 30,000 stacks of cells a year. They are created in the first, those that were created in the first generation, it took 15 minutes to build one cell. Now we reduced it by 2 orders of magnitude. So it takes less than 15 seconds now. That was one of the key parameters that is decisive on the price of the fuel cell, because we also reduced the price of manufacturing fuel cells. Mirai of the first generation, the record 830 kilometers in terms of range for seater car. Generation 2, 5-seater car with a record range covered in public traffic in France, 1,000 kilometers. So we've got effects showing that an electric car does not have to have issues with range, 3 to 5 minutes of filling up in the range like any car today. What is important is that a class high car is actually cheaper than its predecessor. It is the price of the drive that made it possible for us to reduce the price of the car, despite it being a class high from its predecessor. An adequate car, LS 450, Lexus LS costs 450,000. This one is 300,000. So certainly the barrier in this car is not in the drive. Now, the density of power in the fuel, the new generation, cells 4.4 kilowatt per liter. Where can we find Toyota's cells on buses and trucks and forklifts? And of course, in the passenger car, in trains and boats. Our global projects cover different uses, different applications that I will enumerate now, but I would like to tell you also that we belong to Japan H2 Mobility Association, whose task is managing the operations concerning hydrogen economy in Japan, so as not to double the tasks, not to repeat the projects that failed elsewhere, not to waste time or money on something that proved to be a cul-de-sac, a dead-end street. So that is why we create projects that we implement off Japan. The Sora bus that you can see here drives the streets of Tokyo. We used it during the Olympic Games in Tokyo. It founds there is another car that follows the pattern. In Europe, a Portuguese company, Caetano, is the company with which we created a bus that after 15 minutes of tanking has the range of 400 kilometers. The Los Angeles port is the port that, among others, is used by Toyota. 10,000 lorries are used there. It is co-created with us with the state of California as the project of zero-emission port. We've got lorries, we've got forklifts that, of course, are powered with hydrogen. The biggest challenge was to create a lorry, a full-block American lorry with the range of 400 kilometers, 450 kilometers. The distance from one rest point, as required by law, that's 400 kilometers. We can cover that without any issues. The large truck, Japanese one, 600 kilometers tests will start on the roads next year. The project of mass usage of Toyota Mirai, is over 600 vehicles, taxis in Paris. 7-Eleven is the project to reduce energy consumption. Arrangement between 7-Eleven and Toyota is to reduce the CO2 emissions. The project creates the whole network of managing energy on the fuel station together with energy buffers, generator, using, of course, fuel cells with the possibility of charging or taking the current from electric vehicles, including hydrogen ones. Apart from managing energy, so hybrid cars use, well, there is another challenge that is creating a car for distributing goods that at the same time can generate the electricity should there be a low voltage, for example, during an earthquake. Another example, trains. So here's an example of a train that we've been creating for Japanese railways. A similar project is created to European railways in Europe, and stationary use of fuel cells. Energy Observer, a French-based company using Toyota's fuel cells, has created a stationary fuel cell that, for example, shed light on the Eiffel Towers. I think it was 2 months ago. Green color was cast on it, and the fuel that also proposed the boat going around the world using reusable energy sources. I hope that I managed to stick to my time limit. Thank you very much. Should you have any questions, don't hesitate to ask them. Waiting for the speaker to use the microphone, otherwise he is not audible in the booth. It's apparently about hydrogen engines, but we cannot hear much more than that. The Corolla's project surprised not one person in Toyota, but I actually went right to the source. That was a project that was previously co-created by Toyota. We decided that we have a ready-made project, so we are going to use it in most extreme condition in racing. What is the point of using such a drive when you have fuel cells? Well, this is a design that can show you that there is a transitory period for motors. Manufacturing motors gives employment. Well, in our market, I wouldn't like to tell you about numbers, but anyhow, a big proportion of our companies get wages from manufacturing engines, so there can be a transitory period on that. On the other hand, it will give us a greater consumption on hydrogen in the stations. So we will show the stations, look, you've got another source for hydrogen consumption. 2 profits that you can make. I'm thinking about it as a transitory period. A very interesting point of view. I've got a slightly different one when we talk about agricultural machinery, but I believe that's a discussion that would take another conference. We could discuss whether we are going to use agricultural machines using electric motors or whether they're going to burn hydrogen. But I have a question. You've told us about wonderful projects that are being implemented in different countries, and what are Toyota's plans concerning Poland? In Poland, we have 2 projects that are confidential so far. But of course, our ambition is to bring those projects to Poland as well. Well, unfortunately, both projects are subject to confidentiality, so I understand everything is subject to secret. Well, not everything. I did share something with you. Thank you very much. I hope that another speaker has no secrets. He will tell us about a completely new domain that is now inscribed in the decarbonization requirements. Aviation is far and dangerous, but I hope that Dr. Jacek Sawa will persuade us into believing that the experience of the Polish branch of Bratney's company that it will be justified to think about using hydrogen in aviation as well.
As you can see, Toyota has a very wide portfolio of products. Fortunately, it does not produce airplanes, but Let's take a look at this presentation in the context of the policy Fit for 55, that is the taxation of aviation fuel in the context of, for example, imagining traveling to Greece or Spain by train rather than taking a plane, 2-3 hours. Of course, in this context, we might not be quite sure whether we will be actually able to afford such flights. But let's get to the presentation. My company is part of the Raytheon Technologies, made of Collins Aerospace, based in Whitney, Raytheon Intelligence Spaces, and Raytheon Missiles and Defense. The flags indicate the country they're active in. Currently, we have a couple of programs that support Polish defense capabilities. It's the PCHET program and the NAREW program. It's also anti-missile, anti-aircraft defense, and F-35 airplanes that are going to jets that are going to be delivered to Poland. The corporation employs 180,000 employees globally, and about 8,000 of that in Poland. It's quite a large corporation. We're the fourth biggest defense aviation company in the world. And the second largest, Boeing, is not much ahead of us. Our ambition is to be in the big three. I think that after the latest aviation crisis, it's a question of a year or two until we join the top three. As far as our Polish divisions, we have quite a few factories in various locations. We have two R&D centers, one in Rzeszów, the other in Wrocław. We employ there about 600 engineers who concentrate solely on R&D, along with specialized laboratory units. The newest office, it's an office so far that was set up. It's Raytheon Missile Defense in Warsaw. As far as the company itself, Pratt & Whitney, it's a company with a lot of tradition. We've been providing aircraft engines for 96 years. Our division in Rzeszów has been supplying engines for over 80 years. The first engine we provided was in August 1930. That's right before the start of the Second War. We have about 100,000 engines registered, which are currently being used in 13,000 clients. All in all, we've produced over 700,000 aircraft engines, 500,000 of those during the Second World War. The company received special distinction for its war effort, aimed at assisting allies in their victory. As far as our engagement in Poland, you might not be all that connected with the aviation sector, but we have a lot of products, both on the civilian and military side. These are fighter jets, transport planes, training aircraft, helicopters. Also in civil aviation, we have been present since 1936. Polish Airlines purchased Electra planes. We provided engines for those units. We also have Embraer, Boeing de Havilland today, which are equipped with our engines, and our air emergency, which is used so intensively these days, is also equipped with our engines. Now, let's move on to hydrogen issues. Why hydrogen in aviation? As I've said before, all sectors of transport have a certain alternative ahead of them. Aviation is based quite strongly when it comes on various uses of energy, and it's all based on quite sophisticated economic calculations. As we all know, everybody wants to fly. If you remember well, not until all that recently, flying was quite exclusive. Today, pretty much anyone who has 200-300 zloty can fly all over Europe. So this cost pressure is quite high. On the other hand, aviation has to fit in as well, in accordance with the program Fit for 55. So it must play its part in the reduction of global CO2. Here, the company sees the possibility of using new propulsion. In 2016, we've introduced unique turbofan engines, Please imagine that in those 4 or 5 years of use, these engines have allowed us to save so much fuel that we've emitted about 5 million tons of CO2 less than comparable engines of previous generation. What's important? Well, we can say that aviation is not such a great emitter of CO2 because currently it's responsible for 1.6 of global emissions and 14 emissions of global emissions in transport. That's behind road transport. But the number of aviation operations doubles every 15 years. Until 2050, we expect tripling of aviation activity, as you can see, for example, cargo operations. This is these days a very popular method of transport. Perhaps you remember, well, COVID. Transport of vaccines, UPS planes landing at our airports. These were both quite special transports, but we also have quite normal, quite ordinary cargo transports involved as well. And of course, all those issues connected with pressure on the environment are going to translate into the price of tickets. So if we're not going to find any solutions for lowering CO2 emissions, then we'll have to change our habits, and then this train to Greece or Italy 4 hours at night, and we'll be on vacation. Now, how it might look like? Well, these days the situation is that the International Aviation Agency sees a reduction of single fuel consumption by plane at a level about 1.75% year to year. In order to maintain neutrality without increasing the fleet, we have to deal with a 2% savings. So in 10 years, the engine has to be 20% more efficient, which is quite a challenge. As far as other steps that are foreseen is the introduction of sustainable aviation fuel. That is those fuels which offset CO2. That is at the phase of production. We take away CO2, then we emit CO2. By the way, we emit it at the level about 18,000 meters, which stays there for 100 meters or so. There are no trees there which can absorb CO2 that high. Of course, there are attempts to introduce hydrogen at about 20%. When it goes to 2050, hybrid technology, 17%. Solutions when it comes to more customs duties or better traffic organization, about 17%. Well, generally, entire Europe sees a need for change. Unfortunately, in Poland, we don't have an R&D program which would support reductions of emissions purely in aviation. Here, we put our hopes in the Clean Aviation European program, along with clean hydrogen, which is responsible for construction of hydrogen tanks for planes. As far as the future, well, how do we see the future? Well, we see it this way, that we have planes up to 40 passengers or so have a chance of flying based on fuel cells and batteries. All the aircraft which are larger than 50 passengers or so, unfortunately, due to the amount of energy which is required to lift the aircraft and to propel it, let's say flying a certain distance, they will require turbine engines, which will, however, burn hydrogen as fuel. Unfortunately, planes above 200 passengers, when it goes to intercontinental traffic, are not able to either fit hydrogen tanks. There are no technical capabilities right now or in the next 15-20 years to handle those challenges. So most companies see so-called SAF, sustainable fuels, the drop-in type that is put directly into the existing tanks. Boeing declares that until 2030, such fuels will be used 100% in its fleet. Airbus also declared that until 2035, it will introduce the first hydrogen plane. These are the giants. Now, what are we doing? Well, we have nearly 70 years of experience when it comes to burning hydrogen in turbines. The first turbine engine, which was designed for burning hydrogen, was at Whitney 34 for a spy plane, CL-40, CL-400. It was a U-2. Next version after the U-2 was shut down on the Soviet territory, Gali Power, was Cuba involved as well. Most of us know this story. So this type of propulsion was to solve two basic requirements, that is longer range and higher altitude. And the demonstrator of the engine, the test version, was based on the Boeing 3050 engine. The JT3 engine received a pump of liquid hydrogen and a heat exchanger, which heated the liquid hydrogen by bringing in hot air from the compressor, and then the hydrogen was burned in the engine traditionally. And that was just a demonstrator to show that such an operation is possible, and the optimized engine 304 code. In this case, hydrogen was used as the medium by decompressing the hydrogen and heat exchanger and heating it up slightly. The decompressed hydrogen propelled a turbine. That is, hydrogen was the agent in the turbine, which actually put compressor in motion, and the compressor was able to inject the rest of the fuel to obtain propulsion. Now, aside from that, aside from the concept itself, the engine was built. It worked 25 hours on liquid hydrogen in West Palm Beach, in our secret center near Cape Canaveral in Florida. Unfortunately, by the decision of U.S. Air Force, the program was stopped, and that was connected with the Sputnik flight. This little ball flew above the American heads, and they went beep, and then the American Army actually realized they have to shift arms race from Earth to space and concentrate on obtaining appropriate fuel for missiles, so that nuclear missiles can be carried out not by planes. That's why the development went in a certain direction. We, as Pratt Whitney, use this opportunity as well. All the experiences we've obtained in developing hydrogen propulsion was used in building the first space rocket engine, RL-10 engine. It was created for the Saturn program. Later, it was used in the Atlas program. It's being produced until today. Aside from that, after all this program, we had a huge industrial installation for hydrogen production in Florida. It was nearly 32 tons of hydrogen that were produced every day, which, of course, the installation allowed for speeding up the American space program. As far as our own projects, we've been trying to use hydrogen fuel for many years. Of course, it's not that we're alone here, because the entire sector has to go towards the use of hydrogen, because hydrogen needs to be widely available to be successful. But we are researching, we're publishing one of the latest projects I can share. Of course, there are many I can't talk about. It's a project which is founded from the Framework 7, titled AHEAD. Our plant in Rzeszów was responsible for building a special burning chamber and a heat exchanger for hydrogen. It is being financed by the EU budget. There is an official site. You can take a closer look. As far as the main challenges are concerned, this is the last slide. I do hope I've made it on time. As far as the main challenges of hydrogen in aviation, first of all, safety. You choose aviation because you believe you'll fly safely, so safety is most important. The certification regulations which allow us to provide the safety. And the second thing, cost of hydrogen. Of course, economic calculation matters, especially when it comes to private companies. So here we have to compare costs of hydrogen costs with oil, and the cost of purchasing a plane and maintaining the plane, of introducing it into the market. We can also see the supply of green hydrogen as a challenge because, well, I'm not going to give you details how many nuclear plants and various installations you need to generate green hydrogen, but we see certain problem with logistics, both on ground and aboard planes. Perhaps we should start with land vehicles, trains, buses, right, and then move it up. Also, the so-called contrails, that is the water steam being left in the sky, which increase the greenhouse effect and emissions other than CO2, for example, NOx emissions. After all, hydrogen burns at a higher temperature than oil. So generally, I mean, most of us are engineers, and so we can deal with technical issues, the problems of like certification, logistics, legislation. These are really the biggest problem when it comes to hydrogen, and not technical issues such as tanks or combustion. Of course, we need further research when it comes to sulfur, and how it affects durability of elements. But these are normal things that have been done for many years, and this can be easily done. As far as the challenge that we see is going from the phase of examining components such as fuel nozzles, but to examine an entire engine fueled by hydrogen is a huge challenge. We're talking about using a few tons of hydrogen every day to test the engine. So these are the challenges we face. I do hope that both money and need is going to be there to introduce such aviation so that you can fly into Spain, Zanzibar by plane. Thank you very much, and I encourage you to ask questions. I'll be more than happy to answer any of them. Thank you very much. Thank you very much. Actually, you've worried me that the costs of introducing hydrogen is going to be that high, but I assume that if it's a turbine burning hydrogen, then the hydrogen doesn't have to be extremely pure. And if it doesn't have to be all that pure, then it might be cheaper, and the costs will not be all that high, plus the CO2 emissions fees connected with production of regular fuels. Perhaps that will balance that out. Well, first of all, it's difficult to imagine how the market is going to shape, whether we're going to have fuels such as regular petroleum, various kinds, 95, 98, high octane, etc., or perhaps hydrogen manufacturers will concentrate on one type of hydrogen, let's say 509, because it's the easiest to build installations. Now, the second point is whether the hydrogen of the so-called worst quality, whether it will not have any components which will be invasive. I mentioned sulfur, which makes certain elements brittle, but there could be other elements as well, so we have to take that into account. Other elements added in can create emissions. We have a question from the internet. What are the biggest technical issues connected with hydrogen-based engines? I think the hydrogen brittleness, that is appropriate selection of materials to deal with hydrogen, because hydrogen as fuel burns very nicely with high but uniform temperature. Yes, high temperature. The temperature on turbine, actually, it's much lower than in a chamber, because we dilute the combustion gases with air, which makes the combustion gases cools them to a temperature which are acceptable to the revolving parts. Thank you very much.
Ladies and gentlemen, another speaker in this session is Professor Paweł Fuć, representing the Poznań University of Technology. He's going to present to us the possibilities of using hydrogen in public transport. Professor, the floor is yours. We can hear you now. Welcome, ladies and gentlemen, those attending the conference in person and those connected over the internet. The title of my presentation is Hydrogen Application in Public Transport. Ladies and gentlemen, generally speaking, hydrogen is not new. I'm not even talking about its use or attempts at applying it that we've been witnessing over the last 30 years. Even before that, Various efforts were made. Why did they fail? Mostly for the reasons we are facing today. So mostly it was about the generation and distribution of hydrogen. Now we are witnessing an explosion, a boom in the interest of using hydrogen as a fuel that resulted from three aspects. One of them is, of course, environmental protection. The other one is politics, and another one is business or interests of certain parties. So why did the interest with hydrogen appeared? Comparison to the new norm, to the old norm, the new norm, Euro 7, is to reduce CO2 emissions to 30 grams per kilometer. 120 grams is the use of 7 liters of gasoline or petrol. And now counting very simply, it is less than 2 liters per 100 kilometers, according to the new standard. Of course, those manufacturing different sorts of drives need to meet the new standard. There are also limitations concerning NOx's, and we know that it is by no means easy. The same concerns carbon oxide. As for politics, we have two aspects to discuss here. One is the issue of climatic balance. We are obliged by the legislation of the EU, and undoubtedly we have to do something about it. And the other aspect is this is an attempt to get at least partly independent from the supplies of crude oil, from those that say difficult, hard directions. And another thing important for the participants of this forum is business. I presented it here using a bus as an example. It is estimated that by 2030, the market of electrolyzers will be worth 600 billion zlotys. The estimated cost of stations is 1.2 billion zlotys. Now, when we look at the expectations until 2025 and 2030, the investments into the public transportation, making it hydrogenized, it will cost around 1.5 million zlotys. Using hydrogen has been on the increase from 18 megatons to 73. That was in 2022. These are the estimates until 2022. And it is estimated that this hydrogen market could be worth 600 billion zlotys by 2022. As I've mentioned, the interest in hydrogen is not new, and the biggest players in this sense are the USA, Canada, France, Germany, Japan, or Korea. I took the liberty to quote a few examples of buses, of constructions of buses. The closest one is the one by Solaris. That is fitted out with a fuel cell by Ballard of 60 kilowatts, 5 tanks. Its range is 350 kilometers, and the hydrogen consumption is 10 kilograms per 100 kilometers. A twin construction is Citino City Gold, manufactured by a Portuguese company. The distribution of particular components of the system is very similar to that in Solaris. The fuel consumption and range are alike, the only difference being that here Toyota's fuel cell was used instead. Another example is Wrightbus Street Deck Hydroline from Ireland. The range is similar. The number of tanks is also similar. Hydrogen consumption per 100 kilometer is also similar. Another example, again, is very similar. Why have I shown you those bicycles? Technologically speaking, generally speaking, they represent the same level in terms of range,
the amount of hydrogen consumed per 100 kilometers, and so on and so forth. The components that these buses are made of, to a large extent, again, come from the same manufacturers of components, about the axles or the engines, with Ballard being here on the lead in terms of supplying fuel cells, but not only here. Now, ladies and gentlemen, what does it look like in terms of the distribution of particular drives? I mean, the expected distribution of them in 2025 and 2030. In 2025, it is estimated that electric buses powered with hydrogen, of course, via the use of fuel cells, will constitute 27% in 2025, whilst 5 years later it will be 13%. Now, the bigger share will be that of electric buses, as you see. The typically Polish example, as it is produced by the Bydgoszcz-based PESA, so the state-of-the-art solution presented 2 weeks ago during the Traco Railway Affairs in Gdańsk, is a maneuvering locomotive of 720 kilowatts with 167 kilowatt-hour battery and 2 fuel cells of 85 kilowatts each. Ladies and gentlemen, if we wanted to use a rolling stock transporting 150 people, then we would save around 700 tons of CO2 per year. That's more or less an equivalent of 400 passenger cars. If we had 15 such rolling stock arrangements, we would save around 11,000 tons of CO2 per year, which corresponds to the annual output of 6,000 passenger cars. So as you can see, the potential is considerable. Now, in terms of the possibility of using green energy to produce hydrogen used to power those 15 rolling stock sets, we need electrolyzers of the total power of 4 megawatts. But in order to have the 4 megawatts, we need a wind power plant of the total power of 10 megawatts. Hypothetically, now if we wanted to use 3,000 such trains, well, I took this number from the fact that more or less that many trains are used in Poland daily. We would need electrolyzers of the power of 800 megawatts, which is about 200 electrolyzers, or actually an electrolyzers plant of the power of 4 megawatts. This is a bird's eye view onto the recently opened Japanese power plant, electrolysis plant that has electrolyzers of the power of 10 megawatts, and to supply them it needs photovoltaic power, and this power plant produces around 100 kilograms of hydrogen per hour. In Poland, following the pattern of supplying 3,000 trains of the kind mentioned, we would need 400 such power plants, photovoltaic plants in Poland. I would like to show you that as regards buses and electric cars, or developing the hydrogen-related technologies in Poland, We should be aware that a project of a catamaran is actually being implemented around the Tri-City Pro and High Flyer. Participate in it both companies from Gdańsk cooperating with the Polish Academy of Sciences from Krakow. And the participation of mine is the institute that I represent from the Poznań University of Technology. This is the design of the superstructure. Now, probably the question arises of whether certain steps are taken. Of course, the hull is being built. There are certain problems resulting from COVID, from accessibility of materials, from the growing prices of materials and so on, but this project is ongoing. The parameters, the main ones, of course, length 18 meters, beam 735, draft 1.25 meters, and of course displacement 24,000 kilograms. Now, the scheme of the already designed drive is going to, well, this is going to contain 2 electric motors supplied from 2 fuel cells, and for supporting different kinds of systems and for safety. There will also be a CNG generator, although it might be LPG, we don't know it yet, so probably CNG now, and also a generator, the diesel generator. Now, ladies and gentlemen, moving to a slightly more general part of my presentation. Poland emits around 327 megatons of CO2. What can you look for decarbonization options in Poland? Well, actually, there are 4 areas you can look for it in. One is connected with energy and heat production, the other one with electrification, and adjusting to not using CO2-emitting devices, broadly understood in the industry. Then you've got transportation as the 3rd area, and the 4th one is anything that is connected with limiting the emission of CO2 related to heating of the buildings. Transportation, giving the entire amount, is 16%. So replacing combustion engines onto electric engines or hybrid drives constitutes this potential that you could make the most of in terms of the transportation sector. Now, ladies and gentlemen, it is planned or estimated, and again, a lot has been said on this topic already, that in order to arrive at the energy mix until 2050 as desired, well, what you would need to look for is the energy from the wind farms, 73%, 6% would come from solar energy, so from photovoltaic panels, or other methods using the solar energy, and 14% would come from nuclear energy, or atomic energy, as some call it. We know all the while that a lot has been happening in this respect, and we hope that it will turn into some real action. The agreements are being struck with American companies already, so things are in the pipeline. As for the hydrogen production, again, this is a vast topic that has been touched upon already within the conference. What we get now is the so-called gray hydrogen that emits CO2 when produced. Now, hydrogen in Poland is mostly produced and used for the purposes of industry. Those who generate it use it for industrial purposes. There are declarations, though, to the effect that there is no problem to increase the volume of this hydrogen. But the main goal is to generate the so-called blue hydrogen with the possibility of storing CO2, or using the CO2 for other processes so that it is not released directly to the atmosphere. The most beneficial method of obtaining hydrogen would be, of course, generating green hydrogen. But as I shown you on the previous slides, or at least I tried to, it is by no means a challenge now. Taking into account the consumption of energy by a typical electrolyzer, even if the balance is negative, generally speaking, this energy is obtained for free, we can say. Okay, of course, I'm not talking about the footprint, carbon footprint concerning the production of the components for the electrolyzer and all the elements that it needs to be operational. Anyhow, what about hydrogen generation in numbers, and where is this hydrogen taken from? What are the plans for the future? So what is mostly used is natural gas. Because I'm not going to comment on how this natural gas is processed and what this hydrogen is used for. Anyway, in 2050, it is expected and estimated that natural gas will constitute around 70% of the sources of hydrogen. But let's look at electrolyzers. The number will grow from 4% to 22%. This is quite a challenge. We've heard it in multiple presentations, numerous presentations, also those that we heard in the first panel. This is a challenge, technology-wise and finance-wise. So I think that there is still a lot to be done. For major players in Poland that can generate hydrogen are Azoty Group, the largest share of the pie, PGN Orlen, Lotos, and also Jastrzębska Spółka Węglowa. One should point out that we are still talking about hydrogen that is obtained but is also used for internal purposes. In order to generate a kilogram of hydrogen, which method is the most beneficial? Well, forming of methane with absorbing CO2 at the level of 90%, regardless of how it is going to be absorbed. When we talk about supplying electrolyzers with other fuels, as you can see on the right-hand side of the chart, it is 40 or 18%. Coal gasification is 20 kilograms. And also natural gas reforming for capturing is 1% and reforming 9%. So there is potential in order for this gas, for CO2 to be stored. Well, obviously there is, and it is estimated that in the case of CO2 emissions in 2050, when we use all kinds of natural storage options for it, we would have enough storage of it that it would suffice for 600 years. These are the calculations of the Geological Institute from 2020, so I believe it is a reliable source of knowledge. And where can this coal be stored? Of course, in all sorts of formations or some spaces that are remained after the exploration of other minerals and so on, sandstone layers with high porosity, for example. It was mentioned by one of the gentlemen that the distribution is also quite a challenge. There is also the issue of some resistance on the part of the general public against the storing of CO2. Let us hope that we also manage to use the CO2 for some advantageous purposes, like the ones mentioned by one of the speakers at the beginning of the first panel. I also made a calculation, ladies and gentlemen. Professor, would you be as kind as to wrap it up? As regards the prices of the fuel, the most the blue and gray hydrogen constitutes an attractive option, but the fuel station, you pay 40 zlotys per 1 kilogram of hydrogen, so it is even more than I found browsing through different websites. But in order to get the level of 73% of energy from wind, so produce 334 terawatt hours of energy, we would need 24 times more wind farms in 2025 than we need today, than we have today. Now, a definition of a person who is, well, not ecological, average ecological, and pro-ecological, you can compare it and you can see to which group you belong to. Let me just read the private transport for lack of time. The person who is not ecological is a person that has a large car with a big engine that uses it to cover the distance of 200 kilometers per week, occasionally with another person on the car and using air conditioning. Now, to conclude, to my mind, the main challenges ahead are mostly, well, creating clear regulations, transparent regulations. This is happening. We have a cluster, hydrogen cluster. There is an agreement. And another issue is, ladies and gentlemen, the material-related issues. Because if we wanted to use a wind farm of 25 terawatt hours, we would need around 50 million tons of copper, which is 4 times as much as was produced in 2019. And 3.6 million megatons of neodymium, which is 180 times of the current annual production. Thank you very much for your attention. Thank you very much, Professor. I love the conclusions in particular. Very interesting indeed. A lot of items will be elaborated on further on tomorrow. We have a panel on public transportation and financing of hydrogen-related projects. Thank you for those conclusions. I believe we're going to refer to them more than once. And now I'd like to invite you to Dariusz Mroczek's presentation on hydrogen. Well, talking about it, we often talk about ecosystem or a business model. These are the things that emerge when we define new areas and rules of functioning of any new activity. You'll see how the company specializing in power sector produces specialized devices, and you'll see how it shifts to the new challenge, hydrogen technologies.
Good afternoon, Dariusz Mroczek, I represent Rokfin. I do hope that as the last, I'll have 5 minutes more. I've noticed that the biggest challenge is to fit within the time frame on this conference. Well, let's start with a few words about Rokfin. Perhaps everybody's familiar with them, with the company. The company was created in 1985. Currently, it's celebrating its 30th anniversary. The headquarters are located 25 kilometers away from here near Żukowo. We have a production plant of steel constructions in Bydgoszcz, and a smaller one in Gorlice, which deals with production of smaller devices, smaller dimensions. Currently, the company hires about 700 people, about 250 engineers. This is a production profile company. Well, it's the 30th anniversary, so I found the first device produced by Rokfin in 1995 in a garage, so to speak. It's not a device to work with hydrogen. It was a generator for a mixer of a tire-producing company. Since 1994, after starting production, also going to foreign markets, especially in the energy sector, as it was mentioned here, the centralized and dispersed energy, the area of oil and gas, We've manufactured thousands of pieces of auxiliary equipment for steam turbines, gas turbines, compressors, and generators producing electricity. Now, concentrating on the topic of hydrogen, the first device that Rockfin encountered were the sealing oil systems for high-power generators called by hydrogen. This was 1998. 5 years later, we've enriched our portfolio with other systems of generators called with hydrogen, so-called gas systems, that's what the customers call them, and devices used for drying hydrogen. The next piece of equipment, that was 2018 actually, in that gap between 2003 and 2018, we were developing cooperation with global leaders producing hydrogen-cooled generators such as Mitsubishi Power, General Electric, and Siemens. In 2018, we produced a valve module, large one, meant for supplying purified hydrogen, taking out purified ones using absorption method. Last month, we finished production of a new device we didn't produce before. This is a system of supplying hydrogen to be burned in gas turbines and micro power plant of 230 kilowatts. And we are cooperating here with our customer, Mitsubishi Power. The micro plant creates energy from natural gas and water in a high temperature fuel cell. As far as the future, we cooperate with Siemens on designing auxiliary equipment for modules of PEN-type fuel cell systems. We also try to be active as a manufacturer for purifying hydrogen using membrane method. We also participate in the construction of the first commercial hydrogen fueling stations in Poland. The first are to open in 2023. On this slide, you can see the actual prices of fuel. They're increasing, so it's a chance for hydrogen, definitely. Hydrogen can become a more attractive fuel. I've also heard saying that the current price of fuel is higher than price of beer, so it's better to have a beer than to drive. So our area of interest includes the entire system of generating hydrogen for electrolyzer manufacturers. We're also working on our own concepts of hydrogen producing systems. More about that later. A bit of technology, systems of sealing oil generators cooled by hydrogen. Most Polish power plants use such generators. In 90%, the hydrogen we get, the electricity we get, comes from hydrogen-cooled generators. The main shaft of the generator is filled with hydrogen. Why with hydrogen and not air? Well, the generators in an electricity plant turn with 3,000 RPMs, and they have the diameter of a 1.5 meter. And this is circumference of the speed of 850 kilometers an hour. So in such conditions, air becomes hotter. It actually makes the surface of the rotor hotter. That's why hydrogen was chosen. Helium was also considered, but due to cost, it lost to hydrogen, even though helium is not a gas that burns. The oil is provided to the ceilings, and it's there to keep the hydrogen inside the generator. The oil is provided by a pump system of pressure somewhat higher than the pressure of hydrogen inside the generator. So it gets both inside the generator, mixing intensively with hydrogen, and it actually makes its way out of the generator and mixing with air. The mixed sealing oil with air and goes into the so-called barrier tanks and then to the main tank, in which the vacuum pump creates under pressure to get rid of air and dissolved hydrogen. The other system is the gas system, as it's called commonly. It's meant to make up for the losses of hydrogen, about 16 cubic meters a day, and to measure parameters such as pressure, humidity. Other functions are manual evacuation of hydrogen and lowering the pressure of hydrogen, and possibly also emergency evacuation of gas using a quick discharge valve, so that within 10 minutes the pressure in the generator barrel can drop to the level of atmospheric pressure, and so that then the rest of hydrogen can be removed using neutral gas. This system, after changing the shifting valve, can be used for such cleaning of the system. In addition, a ventilator can be installed because circulation of hydrogen in the generator is actually forced by rotor paddles installed directly on the shaft. If the shaft does not have appropriate RPMs, then additional ventilator is started. Each of the system also is equipped with analyzing units which check the content of gases in hydrogen, which is important from the point of view making a decision when the evacuation of gas from the generator should be stopped or going in the other direction, reaching a point when we can say that the hydrogen was provided to the generator and the neutral gas was taken out. Another device are hydrogen dryers. Each generator is provided with a hydrogen dryer. Usually, these are solutions based on silica gel, sometimes also activated alumina is used. Once the dryer is saturated with humidity, then it's connected to the regeneration flow. The dryers that we produce are generated by warm air. Some might say they're dried by hot air, so the moisture taken out of hydrogen is dried up. There are also constructions which regenerate dry using warmed hydrogen. The module we produced in 2018 is used to providing fuel to drying tanks for the Air Liquid company. This is the biggest system which Rokfin has produced. The weight was 37 tons. It was 30 meters long, 5 meters wide, 4 meters high, and it allows for purifying hydrogen in the amount of 57 cubic meters an hour. It's a system, it's a large system for purifying hydrogen from vapor forming. So we get rid of CO2, CO, remnants of methane, and humidity. No, we didn't provide the tanks filled with absorbent. However, we provided the valve module which steers which controls the particular tanks. Another piece of equipment I wanted to show you is microplant producing electric energy from neutral gas and water. It's technology of our Japanese customer, Mitsubishi Power. After 2 years of cooperation, we have started assembly of this device at our location, Mokowo. The gas is provided to fuel cells, and water is provided to vapor producing unit, where we obtain vapor of about 500 degrees of Celsius to initiate the process. The fuel cells requires high temperature, therefore the system has a small turbine which burns some of the gas, and then using the combustion gases heats up the air, which is then compressed by the turbine. On the shaft we have a compressor which compresses the air taken from the surrounding environment. The air is heated up to about 700 degrees, and then it's directed to the tank, in which we have a number of fuel cells, of solid oxide fuel cells. So on one hand, we have natural gas mixed with vapor of 500 degrees, and on the other side we have air. So the neutral gas mixed with steam at higher temperature due to vacuum reforming reaction results in nickel catalysts in the fuel cells production of hydrogen. Then in the catalytic reaction, hydrogen frees up electrons, and in this way electricity is produced. This is quite a complicated process, complicated device. It's a prototype which is going to be tested in the Essen Institute in Germany. 3 similar systems have been manufactured by our customer in Japan. This is the first typical device dedicated to the European market. The plan is to produce micro-power plants of up to 1 megawatts. The efficiency is about 55% compared to gas turbines, about 10% higher. The efficiency when it comes to heat recovery, currently 73%. As we know, in cogenerating systems, it's about 95% or so. So quite a way to go here in order to regain more height from the manufacturing process. So this is what the device looks like. These are pictures I took a few days ago from our production in the tank. The diameter about 3 meters. We have this stack of cells, fuel cells. Then the temperature inside is about 900 degrees Celsius. The entire tank is insulated from the outside, from the inside, in order to handle such difficult working conditions. All the customers we've been working with, all the gas turbine manufacturers are currently working on shifting from gas to hydrogen. This is done gradually, obviously, by first testing using a mixture of neutral gas and hydrogen. Last month we finished production of the first system, which is responsible for actual controlling the gas which is later provided to turbines. For example, Siemens declares until 2023 it will make available technology allowing for burning of pure hydrogen in turbines of up to 60 megawatts, the small and medium-sized turbines, and until 2030 technology of burning pure hydrogen in large industrial turbines of up to 600 megawatts. A couple more pictures from the production plant. We also cooperate with Siemens when it comes to the development of auxiliary systems for electrolyzers, modular ones, which, according to our client, are the biggest module systems in the world when it comes to hydrogen production. Such a model contains 24 fuel cells. It is to produce 325 kilograms of hydrogen per hour. The power supply required 170.5 megawatts. These are to be connected into larger installations, and in this way, whole hydrogen producing plants are to be created. Of course, the assumption is that the energy coming for the production of such hydrogen will come from RES, so high efficiency declared by Siemens, over 75%, which is the highest efficiency I've encountered when it comes to electrolysis-based production. So our task is here to devise equipment, so it's work at fueling stations, so designing equipment for supplying demineralized water for electrolysis process, and designing a closed electrolyzer cooling system. Another device where we try to implement into production is purification of hydrogen using membrane systems. Here we cooperate with a liquid company. This is a less exact technology than absorption mentioned before, but nevertheless this technology is sufficient for cooling purposes. Using this method, hydrogen of over 98% impurity can be produced, much smaller dimensions, smaller manufacturing costs than in the case of PSA technology. And last but not least, the last system we started to work on about a year ago or so. It's a hydrogen generator we've called Green Box because it's supposed to be supplied with green energy. Our first visions dealt with the concept of hydrogen generator, which will produce small amounts of hydrogen, let's say 30 kilograms a day. Why 30? Well, so that we can once a day provide fuel for one bus. Now we've developed this concept based on supplying electrolyzers with photovoltaic energy of 1 megawatt. Such power will allow, provided the weather is good due to quite high variability of energy produced by photovoltaic panels, but this will allow production of 14 kilograms of hydrogen per hour, taking into account our climatic conditions here. In Poland, this average sun exposure about 10,000 kilowatt hours per 1 square kilometer. Such installation could produce 70,000 kilograms to 17 tons of hydrogen a year. We've in this model, in this concept, we've accepted that energy coming from photovoltaic panels will be used only for generating hydrogen electrolyzers. All other devices, such as the module of preparing water, cooling modules, as well as hydrogen compressing units, will be provided by energy coming from the grid. So rather hybrid power model. The grid is about 15% of energy produced, manufactured, stored in the form of compressed hydrogen. Another phase could be a totally off-grid installation, totally cut off from the supply network. However, we are aware that this phase, this project could become too risky for us, too challenging. Therefore, we decided to go for this hybrid model. This is what this plant would look like. Such hydrogen producing unit would look like. This occupies an area of about 2 hectares or so. Here we've modeled 2,500 panels, taking into account that each is 400 watts. As part of execution of technology, probably soon we'll have larger panels, 500-600 watts. So quite likely the amount of needed space for such investment will be smaller. The space needed for hydrogen producing is about quarter of the space needed for photovoltaic panels. Now, is that profitable or not? Well, today production of green hydrogen, all experts say that no, not yet, that green hydrogen is too expensive, it's 2-3 times more expensive than gray or blue hydrogen. However, it is estimated until 2030 or so, the cost of producing green hydrogen will be equal to the costs of producing hydrogen from fossil fuels, mostly due to lowering the cost of producing RAS energy, the development of offshore energy, solar energy, and making more popular electrolysis-based production of hydrogen, compressor units as well. Now, this is supported by the fact that 20 years ago, production of green hydrogen was 40 times more expensive than hydrogen from fossil fuels. 10 years ago, 15 times more expensive. Today, it's 2-3 times more expensive. So one should expect that this prognosis will come true. Thank you very much. That's all from me. Thank you for your attention. Thank you very much, Darek. You've raised a number of questions which we will concentrate on tomorrow, so thank you very much. I would just mention one thing. Dariusz mentioned that they're from Mokowo near Żółkowo. And not that many of you know where that is, but when I think about Rockfin, I think that, something good can be done, something cool can be done in Poland. I'm not sure if you'll ever have an opportunity, but it's worthwhile to visit Rockfin and take a look what such a company can look like in Poland, because very rarely we're able to see such companies in Poland, how one could build from scratch, basically. Remember this first picture, such spectacular production. So this is the end for day one. Tomorrow we'll deal with many issues we've indicated today. We'll develop them further in discussion panels. I think we'll ask some difficult questions, challenging questions. We didn't send questions to our tomorrow's guests, so I think we'll be surprising them. This will be quite interesting because we will want to develop conclusions which were presented during today's presentation. Marek, we would like to invite you for tomorrow at 10 a.m. Here. Yes, these will be mostly debates, fewer presentations. Today was very technical. I think you've learned that hydrogen technology do have their solutions in various pieces of equipment, machinery. And finally, I'd like to thank our partners, our sponsors, Bank Ochrony Środowiska, the main sponsor, Dystra company, and Lotus Group as well. Thank you very much.